Okay, it's going to often be very interesting and useful to be able to find zeros of a given function. And in particular, in this video, we are going to find zeros of a polynomial. Now, there might be different ways that question is asked. So let's talk about different ways that we can describe a zero of a polynomial. So a zero of a polynomial can also be written as the x-intercept of my polynomial, and it can also be written as a root of my polynomial. It is, or they are, the solutions to the equation f of x, so that's my polynomial, set equal to 0. So if you can find the x's that satisfy this equation, you have found the zeros, the x-intercepts, and the roots. Okay, now you've seen this before when maybe solving quadratic equations. So for example, if I said find the zeros for f of x equal to x squared plus 5x plus 6, this is equivalent to solving f of x equals 0. That is, x squared plus 5x plus 6 equals 0, and solve. Now, if this factors on the left, then we're good to go. If not, we can always resort to our quadratic formula. But this factors, so I end up with x plus 2, x plus 3 equals 0. And now I'm going to employ the zero product property, which we've been doing all semester long, and we're going to set each factor to 0 and solve. So when x equals negative 2 and when x equals negative 3, that satisfies the equation f of x equals 0. So here are my zeros for this polynomial. They are also my roots. They are also my x-intercepts. Okay, so let's look at 3 other examples where we might be asked that question and in different ways. Alright, so if I gave you this following function, let's look at number 1, and asked what are the x-intercepts of f of x equals 2 times x minus 2 quantity squared times x plus 3. Now, this is a polynomial, but it's already in factored form. If I ask you to expand it, you could tell me what the degree of this polynomial was, and you could tell me what its end behavior was, which, as we know, is determined by the lead term of my polynomial. However, in this particular problem, we're actually trying to solve f of x equals to 0. Since it's already factored, I set each non-zero factor to 0. Now 2 will never be equal to 0, so I don't consider that factor. So x minus 2 equals 0, or x plus 3 equals 0. X equals 2, x equals negative 3. These are the x-intercepts for this polynomial. Let's see how we would tackle number 2. Here I don't even mention x-intercepts or zeros. I just asked you to solve this particular equation, which, by the way, is equivalent to finding the zeros of this polynomial. Hopefully this thing factors, and as we see, this looks like a squared or a quadratic, and we know how to handle those. X squared, let's see, I think minus 3 x squared plus 2 equals 0. So let's check. If we re-multiply, we get x to the 4th minus 3x squared plus 2x squared gives me a minus x squared. Minus 3 times plus 2 gives me a minus 6. Alright, so this factored nicely. So now I set each factor to 0. X squared minus 3 equals 0. X squared equals 3. Or x squared plus 2 equals 0. X squared equals negative 2. Immediately we see this particular equation has no solution because we cannot square a real number and get a negative 2. So this leaves us just with x squared equals 3. X equals plus or minus the square root of 3. So this is the answer to this equation. Alright, let's look at this last example. Find the zeros of this polynomial. Well, as we've seen, that's equivalent to solving this equation. And if this factors, we're good to go. And it does. I can factor out an x. That leaves behind x squared minus 3x minus 4 equals 0. And if I look further, I see I can factor even more. That is x minus 4, x plus 1 equals 0. I have three factors that I can set equal to 0. The first, x equals 0. The second, x minus 4 equals 0, or x equals 4. And the third, x plus 1 equals 0, or x equals minus 1. These are the zeros of this polynomial. Now, here's something very useful. If you know all the zeros of a polynomial, then you can construct a polynomial with exactly those zeros. So, for example, if I said construct a polynomial with, polynomial with the following zeros. And you can actually construct many different ones, and I'll show you how that can be. Let's say 1, -2, and 3. Well, recall, if 1 is a 0, that means x minus 1 is set equal to 0. We can go backwards, remember, with the zero product property. So one of my factors that was set equal to 0 gave me x equals 1, right? So this means if 1 is a 0, x minus 1 is a factor, right? If x equals -2, let's go backwards. That means x plus 2 equals 0 was one of the factors we set equal to the zero product property, which means x plus 2 is a factor. And if 3 is a 0, then that means we had x minus 3 as one of my factors from the zero product property, so x minus 3 is a factor of my polynomial. So, if I want to construct a polynomial with those factors, f of x equals x minus 1 times x plus 2 times x minus 3 is a polynomial with those zeros in factored form. Now notice I could multiply this polynomial by a constant, 2 maybe, or 3, and it wouldn't change the fact that only these are my zeros, because that coefficient, a non-zero coefficient, will not have any effect on the 0 power, right? So if I were to set this equal to 0, I could go back in that direction, right? I'd set each factor to 0, and I would discover 1 is a 0, -2 is a 0, and 3 is a 0. We usually don't leave it in this form, so we can expand it by multiplying. So x minus 1, let's just multiply this one out. X squared minus x minus 6. Let's keep going. This is x cubed minus x squared minus 6x minus x squared plus x plus 6. Finally, combining like terms, we get x cubed minus 2x squared minus 5x plus 6. This is a polynomial with these three zeros. Now, again, if I had multiplied this whole thing by another number or a constant, 2 or 3 or 4 or -10, it wouldn't have changed the zeros that are already present. It would have changed this function, which would have factored the same way, except with another constant.